Hi, everyone. As I told the dean a few moments ago, I was born in Brooklyn, so I was from Brooklyn before it was cool, and haven't had a chance to come back to give a lecture ever since then. So it's been really wonderful to be here, and I'm really happy that you made the trip, those of you who came from afar, to come see this lecture. How many of you here are members of AEESP? Raise your hand. Okay, good. So if you're a PhD student, if you're a professor, it's unforgivable that you're not an AEESP member. You probably won't get tenure until you join. But if you're a student, you should also join, because it's not just environmental engineering science professors, it's our students too, who are part of this organization. And we have a wonderful conference every other year. And the new one's coming up in Austin, Texas, I believe, in about a year. And so please follow that and follow AEESP, because it's a wonderful resource for creating community among environmental engineers. And so the AEESP lecture is part of this effort to create community, because instead of you traveling to see the lecturer comes and sees you and has interactions with you. And it's been a wonderful day so far meeting people. I'm looking forward to the lightning talks and the poster session and all the conversations that will ensue from there. But part of this, and I have to kind of sing for my supper in a way, is to give you the AEESP Distinguished Lecture. And there are 2 lectures that are offered, and people get to choose them. And since Andrea was the one choosing, you're going to see the one on nature-based systems. But there's another lecture, and you can roll, if you have a time machine, you can go back yesterday, because I gave this lecture at Columbia for a class that had been studying this topic, and it's related to this topic. It's on small scale or distributed treatment systems for potable water reuse. And anyone who's really interested in this can drop me an email. There's a recording of the lecture I gave at Notre Dame a few weeks ago on this topic. I'm also working on a perspective article, possibly in ES&T or another journal, with 4 or 5 other authors. And so that's why it's not done yet. There's a perspective article in ES&T that came out in January about today's lecture. And so if you'd like to find related readings or dig a little deeper into this topic, just look me up. It came out in January and has a very similar title to this. And it's kind of the documentation, so you can see I'm not fully making this stuff up. But these 2 lectures, if you notice the similarity between the title, is looking at this idea that there are water crises out there in the world. And my thesis in these 2 lectures and 2 perspective papers is that the way we did things in the 19th and 20th century isn't good enough anymore. There's a major set of changes coming from the result of development, increases in wealth, changes in the chemicals we use, as well as climate change that's driving us to find new ways to respond to water challenges. And this lecture is looking at this idea that we've developed a series of institutions and industries and regulatory approaches around a certain way of treating water pollution problems. And in the process, we've made it very hard for nature-based systems to find its footing. And I think that's a real shame, because some of the types of challenges that we're now facing require us to expand beyond the unit process mentality of gray infrastructure and embrace green infrastructure, not because it feels good, but because it's more effective, it's more sustainable, it's more resilient, and it's more widely embraced by the community. So that's the underlying message of this talk. Now, to get you to the point of seeing this underlying message, I want to take a trip back in time to one of our predecessors, Abel Wohlman. How many people here know who Abel Wohlman was? Okay. Yeah, it's all us old timers who know. A couple of younger people know. Abel Wohlman was a sanitary engineer. He was really one of the founders of this discipline of environmental engineering. He was a professor at Johns Hopkins University. And one of the things that he thought about was the idea of urban metabolism. And in 1965, he published a paper in Scientific American where he argued that cities were a little like living organisms, in that they took raw materials. In the case of cities, they took in water and food and fossil fuels and energy, and they produced waste. And we lived in this environment, and the job of an environmental engineer was to make sure that that waste was properly managed and that those resources were used effectively. And at the time that Abel Wohlman was writing this article, many, or in some cases most, of the cities in North America did not have organized sewage treatment plants. There were some primary treatment plants, there were some secondary treatment plants, but it was pretty common for wastewater from cities to just flow directly into waterways. And so obviously the Hudson River and the East River and I guess things like many of the waterways in the Hudson and the Potomac and places like that were fouled with the stench of sewage. And so Abel Woolman was kind of starting to advocate for the idea that we need to do a better job taking care of our sewage and our solid wastes and our industrial wastes at that time. And Abel Woolman had a pretty hard time. He and his colleagues were frustrated that not much happened because they knew that there are answers to these problems, but society wasn't ready to make the major investments until something happened. What is that thing that happened? Well, you can see here a picture of the Cuyahoga River outside of Cleveland, and it's on fire. But this is not the first time the river caught on fire. This is something like the 12th time the river caught on fire. And in the late 1960s, the public was used to the idea that the status quo somehow wasn't working, whether it was civil rights, whether it was the Vietnam War, or whether it was the environment. The public thought that the status quo wasn't making sense anymore, and they were ready for change. And so the Clean Water Act got passed in 1972, and over a period of about 20 years, we spent somewhere upwards of $1 trillion building sewage treatment infrastructure with the goal of making our waterways safe for fishing and swimming. And this was a tremendous success. It became possible to go back into the heart of our cities and walk along our waterways. We no longer encountered fish kills and noxious odors and the horrors of the pre-sewage treatment era. But in the process of addressing the problem that Abel Woolman and his contemporaries had identified, we created a series of institutions. And those institutions were things like wastewater utilities and environmental consultants and regulatory agencies and equipment providers. And these organizations became kind of the basis for the way we thought about managing the environment. Now, in many ways, like I told you, that was a really good thing. But it had an unintended consequence of creating a certain amount of path dependency or institutional lock-in so that when new problems were identified, the best way to solve that problem was to add another concrete box to the unit processes that we used for sewage treatment. Take, for example, the problem of nutrient discharges to surface waters. This is a specific example of Washington, D.C., and its efforts to control nitrogen pollution of the Potomac River. What you can see here is that after Washington, D.C. Upgraded its sewage treatment plants, it still had a problem with nitrogen. You can see the loads of nitrogen in terms of millions of pounds in the mid-1990s being pretty high, the population continuing to grow, the red line, and problems with eutrophication and fish kills and poor water quality in the Potomac threatening them. And so what did Washington, D.C. do? They upgraded the Blue Plains treatment plant with biological nutrient removal. And you can see the success here, 75% reduction in nitrogen discharges from Washington, D.C. They spent about $3 billion doing this. This works out to something like $1,500 per person for everyone living in the D.C. area at the time, but this is the way we solve problems. And so when other problems are identified, we often turn to this approach. For example, in the late 1990s, researchers started to notice this phenomena of feminization of fish in effluent-dominated waterways, and it was attributed to things like steroid hormone discharges from wastewater treatment plants. In Switzerland, which you may not think of as a water-scarce country because it's the water tower of Europe, there are a series of rivers in the populated northern part of the country that are essentially effluent-dominated waterways because they receive the effluent of the cities without a lot of dilution. And they saw signs that the levels of steroid hormones and pharmaceuticals were reaching the point where you could see ecological impacts. And so the Swiss turned to the same sort of approach that we used for nutrient control and built advanced treatment plants. You can see here a picture of one in Regendorf, which used technologies like ozone followed by biological activated carbon to degrade these trace organic contaminants and protect the ecosystem of the waterway. They built about 25 of them, probably the red dots on here, and the plans are to build about a total of 100 of them to protect waterways by upgrading this treatment process. And so this phenomena of taking secondary treated wastewater and adding more steps to it is something that we refer to as effluent polishing. And so effluent polishing is this concept that simple biological treatment isn't enough. Sometimes you need to add more unit processes. Because you've created these institutions and this wherewithal and this industry that thinks about building more concrete boxes to polish effluent, that's the way we do it. But today I would like to make the argument that there's another way of doing this. And this other way of doing it involves nature-based systems, and nature-based systems will sometimes be more efficient than these unit processes. But importantly, as we look to the kinds of problems we're likely to face in the coming decades, they may be the main or better approach for solving some of these problems. So to tell you this story about nature-based treatment systems and the way in which I think they can be used to polish effluent at scale, like the size of an entire watershed or a large treatment plant, I want to get small again, and I want to go back in time to the years just after the Clean Water Act was passed, to a place close to me in Berkeley, a place called Martinez. And Martinez is a small city that had a wastewater treatment plant, about 1.5 million gallons a day, that was discharging to the Carquinez Straits. And under the Clean Water Act, they were going to be required to spend a lot of money building a deep outfall to move their wastewater discharge to the place where it would mix with the rest of the bay water. But there was a provision in the Clean Water Act that let Martinez avoid this extra expense by building a constructed wetland. And so Martinez built this constructed wetland. You can see a series of ponds here, a photograph of it here. And it was built with the idea that it maybe provided some habitat. It maybe polished the wastewater, but that wasn't a precondition for it. And it was a lot more expensive than building that discharge pipe. It worked out to about $150 for each person living in Martinez. Remember, $1,500 for nutrient removal in Washington, D.C. So about a tenth of the price. And this was relatively successful because it saved them the money, and it also became a point of community pride. You can see here, there's an interpretive center, and there are school groups that visit, and for the wastewater treatment plant operators, it's the first time they ever saw other human beings interested in what they did and visiting them at work. And so it really became something that they cared about a lot. And this phenomena of building these nature-based treatment systems as a way of addressing small problems and appealing to the public became quite common during the mid-1970s and through the 1980s, to a point where there were a few hundred small wastewater treatment plant constructed wetlands, surface flow wetlands like this, built around the United States. And that experience of building and operating and maintaining these surface flow constructed wetlands, that positive community interaction, gave engineers a certain amount of confidence that they could do something bigger. And so they started to build large treatment plants. And I want to give you a couple of examples of polishing of wastewater at a much larger scale. The first one is the Prado Constructed Wetlands Complex in Southern California along the Santa Ana River. This is where I've done a lot of my research. You can see an aerial photo of it. It used to be a duck hunting facility located behind a dam. There's not a lot of water like this in Southern California, so it was kind of special that they could pond the water and keep it, and it attracted wild waterfowl. But the Santa Ana River was receiving the discharge of a couple of million people upstream in the Inland Empire and some dairies that were in the area. So the nitrate levels in the river were rising to levels that would be out of compliance with drinking water. And the Santa Ana River becomes the drinking water supply of Orange County when it flows downstream. So instead of building a surface water treatment plant to remove the nitrate, they built this 120-hectare wetland site, and the cost of removing the nitrate was only about 5% of what building a surface water treatment plant would have been, because denitrification in wetlands is quite a powerful and fast process, and it worked pretty well. And it's been in operation now for over 30 years. Another example of a large surface wetland is in Texas. You can see it's about 6 times bigger than the Santa Ana facility on Prado. That's because in Texas everything's bigger, right? You know, they love things big in Texas. And this is on the Trinity River. And the Trinity River is a convenient way to get the treated wastewater from the Dallas-Fort Worth Metroplex into the drinking water reservoir of Houston. But the people in Dallas and Fort Worth didn't want to send all of their treated wastewater to Houston because they wanted to recycle it and use it. And so what they did was they built the George W. Shannon Wetlands Project, and that wetlands project captures the effluent-dominated Trinity River about 10 miles downstream of the Dallas-Fort Worth Metroplex, and it's the water, after passing through the wetlands, is pumped around to the reservoirs that are the drinking water supply for the surface water treatment plants in Dallas-Fort Worth. And that facility, one of the things it does is it removes the sediments, because the Trinity River below Dallas-Fort Worth is sediment laden. They have a lot of clay in the soil, so those settle out, and about half of the nutrients are removed, some of them associated with the sediments, some removed by denitrification. But the cost of doing this, instead of building a reservoir and a dam and managing all those sediments, represented about a 75% savings. So you can see now we went from building these small, like hobby wetlands, to building wetlands at the watershed scale. So that's pretty good. Now, do you remember I told you about how those small wetlands, like the ones at Mountain View, at Martinez, were quite attractive to people because the public liked them? Well, the same is true in Texas. This is the John Bunker Sands Wetland Center. It's the partner project for the other one, the Shannon Wetland I showed you. There are 2 of these large mega wetlands on the Trinity River. And this other one has this visitor center here. And you can see it's a beautiful building. It's very popular in the springtime as a place to get married. So it's booked out. So if you want to get married there, you're going to have to get in line. And so whoever heard of a wastewater treatment plant where people, well, you guys would probably get married at a wastewater treatment plant, but most normal people don't want to get married at wastewater treatment plant. This one's attractive enough because it looks out on beautiful bird habitat and a beautiful wetland. So these things are widely appreciated by the public. And in some cases, they even fit an important cultural context, like in New Zealand. So in New Zealand, where the Maori people are co-signers of the constitution that founded the country, there's an interesting approach to water management. And that is that in addition to meeting the numerical discharge standards that we might have to meet here, they also have to do things that are culturally appropriate to the Maori people. And one of the things about the Maori people's view of water is that water that's been used by people for activities and put down a sewer or something like that needs to undergo a purification to go from being considered tapu to noa. And to do that, the water has to percolate through the soil or flow over a series of rocks or move through the environment in one way. So this is the Rotorua treatment plant, an artist's drawing of what was eventually built there. It's a lot nicer than the photos, but you can see that many wastewater treatment plants in New Zealand now use some sort of nature-based treatment system as a final polishing step because it makes sense culturally in their society. So constructed wetlands, built at scale, constructed wetlands, less expensive, constructed wetlands, popular with members of the public, but do they work, right? We're engineers, we care about water quality, we want to build something that's actually going to improve water quality. So let me share some data with you from the Prado wetland, that first wetland I showed you. And these are data on nitrate removal over a period of, about 25 years. And you can see the blue triangle showing you the water going in and the water going out in the orange circles, and you can see something like 75% removal of nitrate. So that's pretty good for removal of nitrate if you think about what it takes to build a denitrification treatment plant. Now, if you're good environmental engineers and you're looking at it, you might notice the y-axis says summer nitrate, and you might remember that denitrification exhibits a very strong temperature dependence. You might say, well, I don't like a treatment system that only works part of the year, but in Southern California, it's relatively warm. And so we see pretty good nitrate removal even in the wintertime, because as it gets colder, other biogeochemical processes take over, and we still see good removal of nitrate. If you're a good environmental engineer, you're saying, okay, nitrate is one nutrient, but maybe I care a little bit more about phosphorus. Does not do a very good job removing phosphorus, because there's no equivalent of denitrification for phosphorus. The only phosphorus uptake in the Prado River is biological uptake, and the plants are not growing all that quickly, so you don't see it. In the Trinity River, we saw about 50% removal of phosphorus because the phosphorus was associated with particles, and the particles were settled in the Santa Ana River. That's not the case. Now, my personal interest in constructed wetlands, and the thing that got me interested in them, was using them to remove trace organic contaminants like pharmaceuticals and endocrine disruptors, that problem I told you about in Switzerland. And when we worked on this problem, when we first started thinking about it, we were very aware of the research in the literature. And so we did a literature review to document the removal of these different pharmaceuticals in constructed wetlands. And we saw an interesting trend. And that trend was most pharmaceuticals could be removed well by constructed wetlands, somewhere around 75%. But there were very few where we saw 100% removal. And that has to do with the realities of the hydraulic condition in the wetland. But mostly there are microbes that can break down these contaminants in a wetland. And there were a few pharmaceuticals, for example, like carbamazepine and clofibrillic acid here, that are barely removed in constructed wetlands. And these are compounds that are known to be resistant to biological wastewater treatment. And these were mostly laboratory studies and very small pilot studies. When we zoomed out and looked at full-scale wetland systems, we often saw a performance that was much worse. So here's some data from a paper from Ann Lightbody. She was a PhD student at MIT who studied the hydraulics of wetlands. And you can see this particular wetland that she was studying, in the cross section, there's one area where the water was flowing about 10 times faster than the rest of the water. It turns out that before that wetland was built, the area had been a farm, and the farm had a road on it. And when they built the wetland, they maybe ripped up the macadam that was the road, but it was still compressed. And so the wetland plants didn't grow there. And so you got channelization. You can see a photo there, what channelization looks like in a wetland. And so something like 80% of the water short-circuited through the wetland along these channels, and had a nominal residence time that was much lower than what the engineers had planned. And we see this over and over with constructed wetlands, that over time, even if you don't have things like farm roads running through your wetland, you see this hydraulic short-circuiting develop because wetlands are nature-based systems. Nature wants to find things like this heterogeneity that comes from channelization, and so wetlands need maintenance. So one of the things we've learned over the years is that when you build a wetland, you don't just build it and walk away. You have to think about a variety of maintenance tools for it. And we and other people have learned tricks of the trade, like building deep zones in wetlands to allow for mixing, to make sure that our macrophytes and large plants are maybe perpendicular to the direction of flow, and also to be very careful about managing the wetlands so there aren't stagnant zones of waters where mosquitoes can breed, because it becomes a vector problem. And in our case, or in the case of the Prado wetlands in Southern California, they even take wetlands out of service in sequential years and dry them out and cut all the wetland plants down and feed them into a wood chipper and start over to fight back against this hydraulic short-circuiting. Or if you prefer, you can burn them, which doesn't make you very popular in Southern California with your local air regulators, but it's a way to cut down on the mass without this labor-intensive process. But the point I'm trying to make here is that constructed wetlands are a technology. They're not something that you just let nature design and walk away from. They take some sort of active management, but they can give you very good performance. But being a little bit frustrated with poor hydraulic performance of surface flow constructed wetlands, we sought out an alternative for operating our wetlands. And I want to tell you about, I guess, the two alternatives that we came up with and that we've developed in my research group over the years and taken to scale. The first one is shown here, and this is something we call a unit process open water wetland. And you can see a close-up. This is an aerial view from a section of the Santa Ana River. You can see up there, we took that section of the Prado wetlands and we ripped out what was there and we installed these 3 rectangular cells. And these rectangular cells have a geotextile liner on the bottom that prevents rooted plants from setting up in them, so we don't get that channelization. But now it's no longer a wetland, it's a shallow basin. It's about 30 centimeters deep and the sun shines through it. And what happens is when the sun shines on water, you get phototransformation of organic compounds and you get photoinactivation of waterborne pathogens. You also get diatoms. Brown diatoms grow on the bottom of the wetland, and these diatoms have very interesting metabolic properties, including the ability to denitrify nitrate and to transform trace organic contaminants. And so my first graduate student who worked on this topic, Justin Jasper, did a wonderful job characterizing these wetlands, making fine mass balances for the wetlands. And this one, you can see the carbon, the nitrogen, and the phosphorus mass balance. The thing that I think was most important to us was that we had about 28, I think these are in units of kilomoles per year coming in, and only 10 coming out. So we're seeing something like that 60, 70% removal like we see in the surface flow constructed wetlands. So this became the idea that we could start building these wetland systems and seeing how they worked. And we were particularly interested in the photochemistry of these systems. And so Karsten Prasa, who's now an assistant professor at associate professor at Johns Hopkins, when he came for his first postdoc with me, it was so much fun. He came for 2 of them. You can see he studied the phototransformation of these antiviral compounds in the wetland. And one of the things that was really exciting to me about this work is that he saw how the combination of phototransformation and microbial biotransformation could lead to metabolic pathways that you wouldn't see if you just had one or the other. So the orange, the part of the molecule that's circled in orange is the part that's amenable to phototransformation. The part that's green is the part that's susceptible to biotransformation. And you can see the compounds breaking down based upon this like 1-2 punch of a different part of the molecule being transformed during the daytime with sunlight, and then the other part of the molecule 24 hours a day with darkness. And then as the molecule changes, it makes it susceptible to other types of transformation reactions. And so these processes can be particularly potent because they employ multiple transformation methods simultaneously. And that's a really fun paper to read, but a little confusing to present to an audience like this, because there's way too many figures, right? The other thing we did was we built these systems at scale. So that aerial photo that you saw a little while ago, Sam Baer, when she was conducting research on this system, was looking at those giant wetlands that you could see out of the window of an airplane in that earlier picture. And what we did was we ran those 3 parallel cells either with a nominal residence time of 2 days in 2014, or we split it into 1, 2, and 4 days in 2015. And as you'd expect, longer hydraulic residence time, better removal of nitrate, right? And also you could see contaminants. So you can see, in this case, atenolol, a beta blocker, one of these heart medications, again, better removal at longer residence times. And carbamazepine, almost no removal at all. And this is that compound, one of those compounds I showed you before from the literature review that was very hard to break down in constructed wetlands, hard to break down in the open water wetland, and hard to break down in wastewater treatment plants. I'm foreshadowing something I'm going to talk about later. But this paper showed that this was an important part of it. And this is the part where Andrea comes into the picture, because one of the important parts of this work was translating the research on these open water wetlands to design guidelines that engineers could use. So Andrea had like a 6-month period between when she finished and when she started here at NYU, and she took on this project of writing up design guidelines for engineers. And I think one of the important lessons that we've had working with these nature-based systems is it's not enough just to study them in the laboratory. It's not enough to build out pilot and demonstration projects. You really have to walk and give something to the engineers so that they feel more comfortable actually designing these things. And this has enabled others to build these constructed wetland systems. So that's the first type of novel constructed wetland that we built. But it wasn't the only kind that we built. We later on came up with a different idea of building something that we call a horizontal levee. And this is a photo of the horizontal levee system that we built in San Leandro in a place called Oraloma. And this project came about because I went to a meeting of our local water utilities. So our wastewater utilities have an annual meeting where they talk about the research they're funding. And a geomorphologist was there, and he was talking about a project designed to protect coastal levees from flooding. And it was called the horizontal levee. And the idea behind the horizontal levee was you build a natural wetland on the water side of a constructed levee, and it protects that levee from storm surges. And you probably know all about that in New York. You have things like oyster reefs and things like that that people consider building to protect levees and shorelines from sea level rise. And the thing that really intrigued me in watching this talk was I didn't know how a wetland would stay alive in San Francisco Bay without a source of water, because we don't get rain between April and October in a normal year. And so you can't have a wetland sustained at a level above the high tide zone. And I asked the geomorphologist how they did this, and he said, oh, we're going to deliver water to the subsurface through a perforated pipe using the wastewater treatment plant that's next to the project. And I said, do you have anyone studying the water quality? And he said, no, we didn't think it was important to study. And I raised my hand. I said, I volunteer. And so I got involved in this project because I thought it was so fascinating that you could actually create nice livable spaces next to flood control infrastructure and purify water at the same time and create attractive wildlife habitat. So this is an architect's schematic view of what it might look like after it's built. And now we have one built in Palo Alto, and it does look a little like this. But you can see up there this idea of the wedge of wetland soil next to a constructed man-made levee and the water percolating in the subsurface. So this is our treatment plant, the Oraloma Sanitary District Treatment Plant, and they had to build a wet weather treatment basin. And so we used the opportunity of building the wet weather treatment basin to build our horizontal levees up here. And so what you can see is this is what they look like after they're built. So it's this sloping topography. We planted them with native sedges and rushes that we had cultivated by a group called Save the Bay, an NGO that specializes in restoring wetlands. So it's not like cattails and bulrush and these kind of invasive species. It's actually native species, and it's very beautiful, especially in the springtime. And this is what it looks like from a top view. So we built it not just as a demonstration project, but as an experimental project with 12 separate cells that were hydraulically isolated from one another, and we could put water in at the top. The influent to the wetland was the effluent from the nearby wastewater treatment plant, and then we could sample in between through a series of pore water peepers. And so we had pore water sampling. The water's flowing about a meter below the surface, so it's pretty easy to get to and sample. And so the idea behind the horizontal levee is that the plants are growing in a layer of sandy loam, and underneath it is this porous media consisting of gravel and sand. And intermixed with the gravel and sand, we have about 3% wood chips. The wood chips serve as a substrate for the microbes, and biofilms form on the outside of the wood chips. And the idea is that eventually the plants grow and they extend their roots into this porous media and they become the source of organic substrate running the microbiology. And so the system looks something like this, where we see our normal progression in redox chemistry, where the aerobes are at the front end, and then we see denitrification, then we see iron reduction, then we see sulfate reduction, and then we even see methanogenesis at the end of the system. And these different systems mean that any contaminant that's moving through the subsurface has to navigate a gauntlet of different redox conditions and microbial communities. So my first PhD student who worked on this was Aidan Cacchetti. Here's Aidan in with some of the plants, and he saw that nitrate was removed within about a meter of entering the wetland, and it was removed mainly by denitrification. He did some beautiful work with stable isotopes to show that it wasn't biological uptake, but rather it was mainly denitrification. There was a little bit of anammox, perhaps. Angela Stiegler's dissertation following Aidan's was looking at trace organic compounds, and you can see that most of the trace organic compounds were also removed in the first 5 meters of the wetland. But surprisingly to us, that compound carbamazepine, the one we were, here's where the pre-shadowing comes in, that was actually removed. And we think that that compound and these two metabolites of antiviral compounds were removed in the sulfate-reducing zone. And I find the sulfate-reducing microbes to be particularly interesting for their microbiology and their underexplored potential for breaking down recalcitrant trace organics. And so that was an interesting outcome of that. And we looked at this, and if you're thinking about it like an engineer, you're saying it's probably a lot more expensive to build that horizontal levee than it was to build the open water wetland, because the open water wetland is just some plastic bags and the water flows on top of them. But this thing has a meter of gravel, and gravel can be kind of expensive to build at scale. And we found that out. It was going to be pretty expensive to use this as a treatment system. But then we had this epiphany that this project could be tied to a nearby project where the city of San Jose and the Santa Clara Valley Water District, now called Valley Water, wanted to do a potable water recycling project. They wanted to take the treated wastewater from the city of San Jose, put it through reverse osmosis, and then put that through advanced oxidation and make it drinking water. But in the process, they were going to have all of this brine, because reverse osmosis only has about 85% recovery, this brine that they'd have to dispose of. And the brine was going to be concentrated because it up-concentrates the nitrate and trace organics by about a factor of 5. And that was going to need treatment. And it turned out that the treatment and disposal of that brine was potentially going to stop the potable water reuse project from happening. So we thought, why don't we take some of the brine from the Silicon Valley Advanced Water Purification Plant, where they were doing the pilot work for this, and truck it up to our wetland and put it through the subsurface wetland. And what we saw was that the nitrate was still removed, but it didn't take 1 meter. It took more like almost all 40 meters to remove the nitrate, because the higher initial concentrations, the salt concentrations changing the microbial communities, and a number of other things that we honestly don't fully understand yet, but something that we're in the process of studying now, because we'd like to build these out at full scale when this potable water reuse project happens. And we're kind of in that process of designing those systems now. While we were talking about this, a number of other issues came up where we wanted to continue to study this. And if you think about this, this system here, bringing a truckload a week up to a distance of about 30 miles got to be quite expensive. When I couldn't convince one of my graduate students to get a commercial trucking license, I had to rethink the project. And what we rethought was, we never liked these first 3 wetland cells here in the first place. So we nuked them and we replaced them with some new cells. We made them smaller so that we needed a smaller volume of water, and we didn't need to truck the water up from San Jose as often to study them. And in the process of designing those, the nasty beast known as PFAS became an issue. And so we also decided to study PFAS. And so here's some of our early results from Anthony DeSalvo's dissertation work. Anthony took one of these wetland cells, and what we did was we divided it into 3 parts. The first part, we didn't add any amendments. Between about 7 and 13 meters, we put in 0.3% activated carbon. And between 13 and 20 meters, we put in about 3% activated carbon. And you can see it does a pretty good job removing the long chain PFAS, but not such a good job removing the shorter chain PFAS. We've also been studying Fluorosorb, functionalized clay, for this capacity. And we're trying to understand what it would cost to remove these. And the take-home message is, like, you could build a subsurface wetland, a horizontal levee that removes the C8s and C6s. It might last for about 10 years, but then you have to think about what to do with these sediments afterwards. Hopefully, by the time 10 or 15 years comes up, we don't have C8s and C6s in our wastewater anymore, but that's something we all have to work on together. Another issue that came up as we were thinking about this is that the levels of trace elements or metals in the wastewater were in excess of the discharge permits to saltwater ecosystems. So John O'Euler's been studying copper and nickel. I'll show you some data from copper. So here you can see the treated wastewater cell. We had this great removal of nitrate and also sulfate. And as the sulfate started to be removed, we removed the copper. And that should make sense to anyone who's had a biogeochemistry class or a water chemistry class. It precipitates out as a copper sulfide, or it sticks to the iron sulfides in the system. When we turn to putting concentrate in, we don't see as good a copper removal because we don't see the sulfate reduction. But we see at least some signs at the end here. You can see we're getting about 50% removal of copper, and this is reproducible in the very last part of the wetland where we start to see some denitrification. So Jono's been very busy with XAF spectroscopy to try to understand what's going on here with the removal of copper in this system. And I'd be happy to talk about this with people later. So that's our adventure in the horizontal levee. So we made two different types of wetlands, the open water wetland, the horizontal levee. I wanted to kind of turn my attention now to some of the broader applications of these systems. So I've talked to you thus far about polishing wastewater, taking treated wastewater and removing trace impurities. But I think there are a whole host of other things we can do now that we've learned how to use constructed wetlands at scale. And one of my big inspirations here is this idea of sponge cities. So you can see here a photograph of me with Kongjian Yu, the landscape architect from Peking University, who came up with the idea of sponge cities. And you can see some of the beautiful sponge city projects built in China, and I encourage you to read about them. This is this idea that we can use nature-based treatment systems to manage floodwaters at scale, and in the process, create beautiful parks that also improve water quality. So when you look at the data from the sponge city projects in China, they show similar types of abilities to remove nutrients and organic matter. And many of them were built at scales similar to the ones I showed you earlier, the ones in Texas and Southern California. Kongjian Yu had a big influence on a lot of people in the world. He died, unfortunately, last year in a plane crash in the Amazon, pursuing his dream of expanding sponge cities to something called Sponge Planet. So I encourage anyone who's interested in learning more about this. He wrote a wonderful piece in Nature Water about a year ago, a little more than a year ago, explaining this idea. And I think it'd be great if someone in here took up the mantle and continued to work on that concept. But in addition to building like nature-based systems to manage floodwaters, I think there's also great potential here to start integrating more technology. So what I'm showing you in this picture are two types of devices that haven't been integrated enough into our nature-based system. The first one is something called a solar bee. And a solar bee is a device that has a solar panel and a pump. And what you can do with this solar panel and pump is you can oxygenate waters that are deoxygenated. You can use that pump to mix water, to create bubble curtains, to do all kinds of things that we don't do now in constructed wetlands, and make them behave a little bit more like conventional wastewater treatment plants and increase their intensity of treatment to make them almost a little bit more like actual treatment plants. The second one is just a simple controller. You've probably seen these kinds of things from research here at NYU or other places, where we can use solar panels and sensors and transducers to send data and to use actuators to open and close valves in different nature-based systems to change residence times, for example. So we shouldn't just think about operating these as passive systems. So I want to end my lecture by coming back to Abel Woolman and urban metabolism. And 60 years ago, Abel Woolman had this vision of how environmental engineers would help solve problems related to urban metabolism. But he couldn't have known what was going to happen as this industry of centralized wastewater treatment was developed. And he couldn't have anticipated some of its needs to continue to change over time. And I want to return back to the Potomac River in Washington, D.C., where I showed you this figure before. And we can all pat ourselves on the back because environmental engineers reduced the amount of nitrate coming out of Washington, D.C.'s sewage treatment plants by 75%. But that didn't solve the problem. So what you can see in this figure here is a number of millions of pounds of nitrogen at a place called Chain Bridge, which is upstream of Washington, D.C. in the Potomac. And you can see it's somewhere around 50 million pounds a year. And you can see Washington, D.C. is now only releasing about 5 million pounds a year. So Washington, D.C. is only today accounting for about 10% of the nitrogen coming down the Potomac. The other 90% is coming from upstream from non-point sources like agriculture. You're not going to solve the non-point source pollution problem by building more sewage treatment plants, but you might be able to start treating it with nature-based systems. So you thought you were this is I'm sorry, I meant to put this at the beginning. This is that wetland paper if you're interested in reading more about this lecture. You thought you were coming to the AEESP lecture, but you're actually coming to just another stop on the David Sedlak book tour. This is the first book I wrote. It's called Water 4.0. It came out in 2015. My mom liked it. She read it. Lots of students who don't have environmental engineering majors have liked this book very much and learned from it. But for this audience, I recommend Water for All, the new book, the 2023 book. It has longer words in it, and it has concepts that might be familiar to environmental engineers. And so I'm here to kind of tell you about it, and maybe you're interested in it now. And so you don't feel guilty about buying it from Amazon. I got the publisher to give us a 30% discount QR code. So it's about the same as what Amazon costs. I'm so embarrassed by that. But that's the way the world works today for that book. But I wanted to just end with a few final thoughts. The first final thought I had is none of this research I told you about today would be possible without a number of people. Some of these people are utilities like Valley Water and Oraloma Sanitary District, and they've been our great partners in these nature-based systems. Some of them are NGOs like Save the Bay, and some of them and SFEI, and some of them are federal funding agencies, EPA, NSF, Sea Grant, and USGS. And when we disinvest in science at the federal level, we make we slow our progress to solving environmental problems. We damage our economy. We make our communities less resilient, and we compromise our health and environment. Final thoughts, constructed wetlands. I hope I convinced you that they're reliable, cost-effective means of effluent polishing and not just something that a hippie from Berkeley tells you about. They provide ancillary benefits such as habitat creation and flood protection. There are many opportunities for you to get involved in research and development, studying removal mechanisms, coming up with alternative designs, and maybe developing better kinds of control systems for them. And finally, effluent polishing in these kinds of wetlands are certainly something that can be applied to other pernicious kinds of tough environmental problems. With that, I thank you for your attention and look forward to a discussion. Can the first question be from a student?
Yes, and we have a mic here. So if anyone has questions, perfect. We have one in the middle. Raise your hands and we can get you.
Thank you for the great talk. I have two related questions. One is, thank you so much.
Okay.
Thank you.
Yeah.
I really appreciate it.
Fortune favors a bold. No, that doesn't.
Thank you. My question is about the sensors that you mentioned. Do you have a real-time monitoring for water quality parameters like pH, dissolved oxygen? And the next one is about heavy metals that you mentioned. Do you happen to keep track on heavy metals like lead?
Yeah, so first of all, sensors at the Prado wetlands, we did put a conventional sensor package together, conductivity, pH, dissolved oxygen. I think that was
Temperature, maybe?
temperature. Thank you. And it was fine, and it was on telemetry, and we also have that at Orloma. But I think the next step is combining the sensors with actuators so we can open and close valves and adjust residence times, and we haven't gotten there yet, but I'd like to go there in the future. In terms of metals, lead specifically has not been an issue because the US got a lot of the lead out of our wastewater treatment plants, and what goes into them probably ends up more in the activated sludge. For us, the metals that drive things have been copper, nickel, and zinc, because the surface water discharge regulations are so stringent, and wastewater is actually pretty close to those levels. And that's what Jono's been studying now, and we're thinking about this kind of sulfide-based removal. The plants don't take them up very much, and they don't really stick to the biofilms on the plants, so creating these micro reducing zones and relying upon sulfide and possibly iron oxides as sorbents seems like the way to go. The things that make it a little hard is that treated wastewater has lots of chelating agents that compete for complexation sites. It might be easier in stormwater.
Thank you so much, and thanks again for the book.
You're welcome. It's already signed, okay? Now it can be from anyone because there's no more books. Sorry. Yeah.
Yeah, my name is Yang Dem from Montclair State University.
Yeah.
My name is Yang Dem from Montclair State University. So that is the excellent lecture with insightful information. I have two questions, actually can combine into one. So in most cases, constructed wetlands, my understanding is there are multiple functional infrastructure. So water purification, contaminant removal, that's one of them.
Yeah.
So in order to design, operate one, I say, successful, effective wetland like that, what are your opinions about, as we as environmental engineers work together with the landscape architect, urban planners, like,
Yeah.
Dr. Yu,
Yeah.
And during this collaboration, I just wonder, how could the leadership be structured to achieve all functions met?
Yeah, I mean, I think it's one of the challenging forefronts of this is that it's not just a design that you can plug and play. You need to look at the specific context, and oftentimes this involves engaging the community to see what they want. Like, for example, when we built the first horizontal levee in Palo Alto, the community wanted to have bird watching. That was one of their highest priorities, and water quality was a secondary concern. And so they didn't want to be able to see all the water sampling equipment. So much less treatment in that system than habitat selection. So working with not only landscape architects, but community members seems to be an important part of tailoring the wetland to the specific application. And for us as engineers, this is like a learning process because we're just now learning how to think that way. But I've actually really found one of the greatest things about working with landscape architects is their renderings of projects, because we make schematics, like you saw my cross sections. They make beautiful drawings and allow people to see what's possible, and that really inspires the community.
Thank you.
Yeah. Yeah.
Hi, my name is Linda. I'm from City College, New York. I'm from California. So thank you. Thank you, Andrea. In California, we're very progressive in water reuse and reusing or water reclamation. But in New York State, for example, they are very stringent in using treated wastewater. Is there any advice from you that could maybe help with convincing people to reuse treated wastewater?
Sure. So I see the applications are going to depend upon the local context. And in the case of the Northeast, one of the big drivers is going to be nutrients and not water quantity. So it offers a low-cost way of removing nutrients. And so Florida, which is not a particularly environmentally progressive state, is really focused on nitrogen and phosphorus, and they're one of the leaders in constructed wetlands, not for water quality or effluent polishing as much as nutrient control. So we should look to maybe other states and other parts of the country that have made progress on these areas. I think one of the big challenges with nature-based systems in the Northeast is the seasons play a big role, and our regulations are meant to have like meeting quarterly averages, and nature-based systems are not that effective when they freeze. And so there's a question of whether compliance could be focused towards summertime, if that's the key time for algal growth, for example, or whether there has to be 12 months a year of continuous performance. And these are things that you all are going to have to work with. Other questions? Yeah.
Hello, Elodie Passport from Rutgers now. I see the word reliable in your first sentence, and I think when you look at concentration reduction of a variety of contaminants in full-scale wetlands, they are quite variable. So what do you think are the best or the most effective steps to get reliable reduction efficiencies?
Okay, Elodie, you caught me. Potentially reliable. I think I talked, and I specifically wanted to talk about this issue of hydraulic short circuiting, which is the big gorilla in the room of nature-based systems, especially flowing ones. And so, you know, in addition to an active maintenance program to minimize hydraulic short circuiting, there are things like having separate cells where the water has to pass over a weir and through a pipe so it can mix again, and having deep zones, things like this that we're all familiar with. But they become reliable when they're engineered. And there's this long discussion, which you're probably familiar with, the Odom school of if you build it, they will come. And that makes sense if you're trying to get diversity of species as an ecologist. But if you're trying to get treatment performance as an engineer, you want long rectangular basins with nothing in them. That's why we had the open water wetlands. Or you want fluid flow through porous media. That's why we had subsurface wetlands. When you have a surface flow wetland, you really have to think serpentine flow patterns and going after that short circuiting. I think that makes a big difference. Yeah.
Hi, I'm Yiming Zhang from New Jersey Institute of Technology, NJIT, and I really liked when during your presentation you showed all of your or whatever PhD students or postdoc, you put a very cute and interesting headshot under the what the work they are doing. They are very smiling and enjoy the work that they are doing, and I really feel that vibe when you're trying to convey all the context during your
They were all by AI, yeah.
Yeah, but so my question is all about, you talked about the nature-based water treatment plan, and what's the final goal for the nature-based water treatment plan? Is that we need to combine with a traditional water treatment system with a nature-based system, or we will just remove all the traditional methods?
No, I would never be that naive. I think of an environmental engineer like a painter with a palette of paints, and maybe right now we only have primary colors, and nature-based systems allows us to expand our horizon of colors and paint in different ways. And I think especially as we get to problems of the watershed scale, the non-point source pollution, maybe some of this effluent polishing also. I mean, I think that these brines from recycling projects, there really aren't too many unit processes that can treat them well. And so I see it as kind of like just more alternatives for us, and recognizing that we tend to lock in approaches by creating institutions that support them. And we need to work a little harder to broaden the spectrum of things that we can do.
And yes, and another one point I want to add is when you mentioned about the nature-based water treatment plan, and you said maybe from the economic perspective, organizing a wedding or welcoming the tourists to go to the water treatment plant will be another approach to get more fundings or money to do more research on that. It's really helpful, and I really like that part.
Multi-benefit infrastructure is the buzzword. We did some work with some social scientists, some multi-criteria decision analysis, and one of the things, like for dealing with nitrogen in San Francisco Bay, one of the approaches that scored the highest was the horizontal levee, because people perceived it as also addressing sea level rise. And so we know that we're going to have to spend many billions of dollars on those two problems. It feels right to people, the idea that maybe the investments work, both of them work on the same problem. I'm not sure if that's true yet, but at least that's the perception among decision makers.
Yes, thank you so much.
Oh yeah, one more question.
Okay, yeah. Thank you for the wonderful talk. So one thing I've been thinking about is that a wetland is a very subtropical kind of habitat. So I'm wondering what kind of nature-based water treatment you would think would be appropriate for a colder climate, like some place where in the winter open water may be frozen or very low
So
flow.
if you pick up that article, the perspective article, I talk about the long history in Germany and now in France of subsurface wetlands where you have like macrophytes penetrating into gravel and stones, and those systems are more resilient in places that have harsh winters. So in these German and French systems, the Central European model, there's like primary wastewater treatment coupled to biological treatment in the wetland, and those have been stable for many decades. So I think there are things that are appropriate for colder climates, and a long experience with them. They're not as popular in the United States.
Thank you.
Cool. Thanks, everyone. Thanks for the questions. And one more round of applause for our speaker, David. We're going to take a quick break, like 10 minutes or less to reset.